So in this video, I want to show an example of using virtual memory. So as an example, suppose we have a system has a virtual address space of a 8 kilobyte, where the page size is 1 kilobyte. So basically, we have the 8 pages. And a physical address space of 4 kilobyte, and the system used the byte addressing. So from the information there, you can see that we have the total number of virtual page can be a 2 power 13. So that's gonna be a 8 kilobyte divided by a size of 1 kilobyte. That's the 2 power 10. So it's a 2 power 3. That's 8 virtual pages. A virtual address. So you can see that a virtual address have a 13 bit. That's the 2 kilobyte, so it's a 2 power 13. So the number of bits required to represent one address in the virtual memory is going to be a 13 bit. And from the calculation right here, we can see that we need to have the 3 bit for the page address field, and also the remaining 10 bit for the offset within one page. Because we have the size of the page is going to be a 1 kilobyte or 1024. Also, we can see that a physical memory address requires a 12 bit because that's equal to 4 kilobyte, and the first 2 bits gonna be for the page frame, and the remaining 10 bits gonna be for the offset within a one page frame. Okay, so here's a graphical representation of the virtual memory address. So we can see that that require 13 bits for virtual address, 3 bits for the page, and 10 bits for the offset. On the other hand, the physical address, we have the 12 bit, 2 for the page frame, and 10 bits for the offset. Okay. So now suppose we have a page table below, and what happened when the CPU generate a address of 59 in decimal. So basically, we can transform into binary or in hexadecimal, just 1553 in hexadecimal. Okay, so this is the page table right here. We have the page number right here, and that's the frame, the valid bit. All right. So from what happened when the CPU generate the address 5459 in decimal, it means we have the address in binary representation gonna be a 13 bit. Right here, and also you can see that in the hexadecimal, the same right here. So in a virtual address, we have the 13 bit right here, 3 first bit right here, or 3 high order bit of the virtual address right here. Gonna be a this bit 101. So gonna be represent the the page, and also the remaining 10 bit right here gonna be represent the offset. Okay, so you can see that the first the high order 3 bit gonna be have the value of 101, so that corresponding the value of 5, and that's gonna be represent the page number in the page table. All right, so what does that mean? It means by looking at the address of 101010101 and 0011. Okay, so we're gonna be we're gonna convert this virtual address into the physical address. Okay, so how can we do that? We do that by looking at the first 3 bits of the virtual. That's gonna be corresponding to value of 5. So that's a page number. That's a 5. So by looking at the value of page right here and looking at the page table right here, so 5 corresponding to the page frame of 1. So page frame of 1 gonna be represented by 2 bits in the physical address. So we can have that the number 1 gonna represent by a 2 bit 01. That's corresponding to the value of the frame right here. That's the 01. Okay, so in physical address, you can see that it's gonna convert into the value of 553. Okay, So that's how we convert between the virtual memory to the a physical address using the page table. All right. The next question is that what happens when the CPU generate address of 1000 and 100. Okay, so this some address. This the virtual address have the 13 bit, and similar with the approach we have before. So basically, we take the first 3 bits right here. That's corresponding to the value of 4. So 4, by looking at that's gonna be the page number right here, 4, and looking at the page table right here, 4 have the no frame in there. So in this case, we have the fault, okay, because there's no page of there's no page frame in the page table to looking at. So in this case, we have the fault, okay. So we said earlier that the effective access time, that EAT, take all level of memory into consideration. Therefore, virtual memory also a factor of the calculation, and we also have to consider page table access as well. Suppose we have the main memory access take a 200 nanosecond. The page fault rate is 1%. So 99% gonna have no problem, but 1% gonna have the problem that we cannot have a reference in the page table. So and also we assume that it takes 10 milliseconds to load a page from the disk. So in general, we can have the formula for the ETA equal to 0.99. So that the percentage that the page is not fault, and it's take a 200 nanosecond to get into the page table, and also 200 nanosecond to get into the memory. Excuse me. And the remaining right here get the 1%. That's gonna required to take the 10 milliseconds to load a page from the disk. Okay, so that's the time to go to the disk. By atom up, they have the EAT equal to 100.396 nanosecond. Okay, so that's pretty good number. You can see that even if we have no page fault, the EAT would be a 400 nanosecond. So in this case, you have no page fault. So this term equal to 0, and this equal to 1 time with the 200 and plus 200. That's a 400 nanosecond right here. Okay, in this case, because the memory is always read twice, the first one is to access the page table, the second one to load the page from the memory. So that's going to take try up 200 nanosecond. Also, we can see that because the page table are read constantly, it makes sense to keep them in a special cache. That's called a translation look aside buffer, TLB. So basically, TLB a special associative cache that store the mapping of virtual page to the physical pages. On the other approach, that to the virtual memory is use of a segmentation. So in this case, instead of dividing memory into equal size pages, virtual address space is divided into the virtual length segment, and often under the control of the programmer. So basically, a segment is located through its entry in a segment table that contain the segment memory location and a bound limit that indicate the size of the segment. So after a page fault, the operating system searches for a location in the memory large enough to hold the segment that is retrieved from the disk. Okay.